So at this point, the difficulty is going to jump quite considerably because I'm actually going to start teaching material. So good luck. Let's start with measurability, which is the least fun topic in analysis. Unless you really like measure theory, then I'm sorry. Strong measurability and Blockner spaces. I think it's chapter 1 or 2 in the notes. Maybe it's chapter 2. It doesn't matter. I hope everybody's done measure theory. If you haven't done measure theory before, you're going to have trouble here. But I don't like telling people they can't do something. But if you haven't done measure theory, you're going to have a lot of trouble here. Same with functional analysis. If you haven't done Banach spaces before, this is not going to work. But yeah, measure theory. We're going to start with some basic Banach-valued functions and then build up to the more complicated ones, just to get some notation, to get some feeling for how you even notate Banach-valued functions. Let's start with a measurable space. Not a measure space, but a measurable space. So it's a set with a sigma algebra, but no measure, not yet. And we'll let X be a Banach space. By the way, I'm going to abbreviate, let thing be thing by just, thing, colon, thing. This is just my short way of writing let this be that, yeah? So we have a measurable space and a Banach space over a scalar field, which I'm going to call K because K is either R or C. And I think I've said that enough now. You're familiar with what K is. And let's look at a X-valued function. Oops, no, I don't want that. I want a scalar function. Let's consider a scalar valued function. And let's consider a vector, bold X. And we define the most simple kind of Banach-valued function, write it as f tensor X, using this tensor notation. This is an X-valued function on the measure space or measurable space S. We define this as follows. This is basically just taking the scalar valued function and placing it in the direction of X. So you've got your vector X and you've got a scalar valued function, and instead of the one-dimensional target that you started with, you move it into that direction. I've got on my notes that I have to draw a diagram here, and this diagram is going to look absolutely awful, but I hope it can get across what this should be doing and how you can think about it. If you imagine a scalar valued function here, something like sine, and if you have, say your vector space is R2, and you have your vector X, then this is going to give you a function on R. And now the range is two-dimensional, so I have to try to draw a 2D range here, something like that. Imagine you have like R2 sitting at every point. Say if this is X, and I draw a little X everywhere here, draw this X line, then your function is going to look something like this in that direction, roughly. Does that picture make any sense at all? It makes sense in my head. All right, I've got some thumbs up. This is good. Okay. This function is your f tensor X. And just to note something that's completely obvious is that f tensor X of S is contained in the span of X for all S. Very clear. In a sense, this is a one-dimensional function. But because your Banach space X can be very large, this direction that your function is in can be anywhere. Yeah. Simplest kind of function. And we're going to use this tensor notation all the time. I just want people to be comfortable with that. The next simplest function are the simple functions. Now, you remember simple functions from measure theory. These are the ones that are just given by linear combinations of characteristic functions, finite linear combinations. So a function g, bold g, from s to x is called simple if there exists a finite collection of pairwise disjoint measurable. Of course, measurable here means A measurable because we're dealing with a measurable space SA where A is the sigma algebra. So a finite collection of pairwise disjoint measurable sets S1 through to Sn and non-zero vectors x1 up to xn in the vector space, the Banach space I should say, such that G is given as the linear combination, sum from 1 to n, of the characteristic function of Sn, tensor the vector xn, using the notation that we introduced before. I'm not going to try to draw this. I mean, that's probably the only diagram I'm going to draw. Everything's infinite dimensional. This R2 example is not good. So you've got your disjoint measurable sets S1 up to Sn, and for each of these sets, you have a vector. And so your function is given by pointing at that vector on these sets. And I've just made the assumptions of pairwise disjoint and non-zero vectors just to make things technically simpler. So there's no redundancy in this representation. I should also say that these vectors are pairwise distinct, and I haven't, and I probably should, but it's not really a big deal. These are simple functions. We let sigma sx or sigma sub a sx be the vector space of simple functions, simple x-valued functions. This is just a vector space. There's no norm or anything. All of these sums make sense because they're only finite sums. You never have to think about convergence. In fact, this definition makes sense when X is just a vector space. We haven't used any Banach structure here, but I want to stick with Banach spaces throughout. So think about Banach. And another sort of trivial note is that G of S is contained in the span of all the vectors x1 up to xn for all S in S. In fact, for every S, you're only going to have at most one of these vectors that you're in the span of. But you should think of this function globally. This function's got a finite dimensional span. If X is infinite dimensional, you don't have any control on how big n can be. N is finite, but it can be arbitrarily large. So simple functions are finite dimensional functions. They've got finite dimensional spans. Of course, not every finite dimensional span function is simple, but these are the simplest ones. And as in measure theory, we want to use simple functions as much as possible. We want to approximate everything by simple functions and then do all of our arguments on simple functions because they're simple, right? So the next thing we need to talk about is measurable functions. So we go from the simplest possible functions to the most complicated possible functions. Does anybody remember the definition of measurable from measure theory? Somebody should shout out and tell me. Audience participation, sorry. Or not.
So you want pre-images of things to be measurable?
Yeah, that's one definition, and it's a good one. Pre-images of measurable sets are measurable.
Yeah.
Any other definitions?
That's
the main one.
To be the pointwise limit of a sequence of simple functions, right?
Yeah, that's exactly the second definition I wanted. Yeah, you can take that as a definition, although these are two equivalent properties for scalar valued functions. I've already given away the game here. They're not equivalent for Banach valued functions, right? This is a big definition. If you've read the notes, you've seen it already. Your function f, vector valued function, is measurable if for every Borel set B in the target, the pre-image, F is bold, of this Borel set is measurable. By that I mean it's in A. This is the classic definition of measurability. It still persists. This is what we call measurable. We also have a notion of strongly measurable, which is stronger, also called Bochner measurable, because I think Bochner invented it. If F is the pointwise limit of simple functions. So by that I mean there exists a sequence Fn. This sequence is in the set of simple functions such that Fn converges to F everywhere. So I should write that actually as, where's my eraser? Why is it not erasing? I have technical issues on my own computer here. For some reason, my tablet doesn't want me to erase this. For all S in the measure space, Fn of S converges to Fs. So there's pointwise convergence everywhere, not almost everywhere, just everywhere. We don't have any measure in play yet, so we can't say almost everywhere. We just have a sigma algebra. So that's strongly measurable. And as was pointed out, in the scalar valued setting, these two things are equivalent. Being measurable is equivalent to being a pointwise limit of simple functions. We have a third definition, weakly measurable. If for every functionals are now appearing, functional x star in the dual of x. I hope people are comfortable with dual spaces. The dual space of a Banach space is the set of all continuous linear functionals into the scalar field. Okay. Weakly measurable means for every functional, the scalar valued function, which is denoted by bracket f x star. I'll say in a minute what that is, but you can probably guess. This scalar valued function has to be measurable for every functional x star. This function is defined as follows. So for every s, you take f of s, which is a vector in x. You take the functional x star, and you apply the functional to the vector. So this is a pointwise evaluation of a vector valued function against a functional, and it gives you a scalar valued function. Weak measurability says that all of these scalar valued functions are measurable. This is typical in functional analysis. So a weak version of a property is a property that holds when you test against every functional. Basically, for every property you can define on scalar valued things, you can define a corresponding weak version on Banach valued things by testing against functionals. This idea is going to come up over and over again. So, yeah. Okay, that's all the measurability. So measurability is pre-images of Borel sets are measurable. We implicitly use the Borel sigma algebra on a Banach space. So this is basically saying the pre-image of every measurable set is measurable. Strong measurability is being the pointwise limit of simple functions. And weak measurability is test against every functional, those scalar valued functions measurable. Okay. We're going to call the set of measurable functions MSX. Strongly measurable is SMSX. And weakly measurable, you could probably guess what we're going to call that. We need to give all of those a name. So the first exercise I'm going to give you, by the way, the notes are full of exercises. The exam questions are going to be taken from these for bond students, so you can start preparing now. And the first exercise I'm giving you in the notes is to show that strongly measurable implies measurable, and that implies weakly measurable. you can probably do that in your head if you're used to measure theory. So being the limit of simple functions implies pre-image of Borel sets is Borel, and that implies the measurability property of these scalar valued testing against functional functions. So if X is finite dimensional, I'll write FD. This is standard abbreviation for finite dimensional. Then these sets are equal. In particular, in the scalar valued one-dimensional setting, strong measurability is measurability, which is weak measurability. When you do this for finite dimensional things, you can basically restrict to the individual dimensions and just add up a finite number of things and you get your result. This generally works for finite dimensional spaces. You can take a scalar result and just add it up in a basis or something. But generally, these inclusions are strict in general, but it's not too general. It's not too bad. So let's prove a theorem called the Pettis measurability theorem. And I have to say, I didn't appreciate how important this theorem was until I prepared the notes for this course, because I was just using it constantly in proving everything. So it's, yeah, surprisingly important. A function f valued in x is strongly measurable if and only if it is weakly measurable and we need a bit more. It's not going to come from weak measurability. And separably valued. What do I mean by separably valued? What I mean is there exists a separable subspace x prime of x. I'll say what I mean by separable in case you've forgotten. There exists a separable subspace of x such that f actually just maps into x prime. So f doesn't necessarily see all of x, it just sees a separable subspace of x. What does separable mean? Anybody remember what separable means?
That there exists a countable dense subspace.
Yep,
Subset.
there exists a countable dense subset. And it's a common assumption to make on a Banach space that it's separable, right? For this theorem, we don't need that the Banach space is separable. We just need that the function only sees a separable subspace. So you could basically assume from the beginning that f mapped into a separable Banach space. You could replace x with x prime, and you wouldn't lose any information on f. So strong measurability basically is weak measurability, as long as your function is valued in a separable Banach space. And this is if and only if. And I'll just add a little corollary. In particular, my pen doesn't want to change color. Okay, we're doing it in red. In particular, if x is separable, then strong measurability is the same as weak measurability. And in particular, is the same as measurability. Because if we look up at this chain of inclusions, if the smallest one is equal to the largest one, then they're all equal. So when we deal with separable Banach spaces, which we often do, you don't have to think of this distinction between measurability and strong measurability and weak measurability. And in fact, the nicest one of these notions to deal with is weak measurability, because that lets you reduce everything down to scalar valued analysis. So when your Banach spaces are separable, you can sort of think, yeah, this is sort of like scalar valued, from the viewpoint of measurability, at least, which is the most basic thing. So how am I going for time? When is this lecture supposed to finish? 11:45? 11:50? I think I said 11:45. Christoph, what's the policy here?
It should be twice 45 minutes. I think in Zoom times everything is allowed, but normally...
if it's 45 minutes before and after break, then it should finish at
and then you do
55 past.
15-minute break, and then you stop on the hour, but you do a 10 minutes break. So
Oh, I could do 10. I could do 15 minutes next time.
Yeah.
Okay, we'll finish by 12. I want to do the proof of this theorem. We might have to skip some bits. It depends on how slow I go, but let's see. It's certainly in the notes. So if I end up not giving every detail, you go and read it in the notes. I'll try to get all of the tricky bits out of the way. Let's do our first proof. It's a big moment for this course. Unlike a blackboard, I can't keep everything on the screen at once. This is really awkward. I hope everybody remembers what this theorem is. Okay, so let's start with strong measurability implies weak measurability. This was part of the exercise from before, so I'm not going to do it. I'm going to show now that strong measurability implies weak measurability and separably valued. The weak measurability is free. We have that already. Show that strong measurability implies separably valued. This is where we use a bit of work. So what does it mean to be strongly measurable? It means that there exists a sequence of simple functions that approximate our function. So since f is strongly measurable, there exists a sequence fn of simple functions such that fn converges to f pointwise. Okay, so let's let xn be the span of fn. We're going to construct a separable subspace out of these spans of the simple approximation functions. So xn is the span of fn. Since fn is simple, we have that xn is finite dimensional. Fn just comes from a finite sequence of vectors. Remember that the range of Fn is contained in the span of these vectors x1 up to xn used in the definition of the simple function. So it has finite dimensional span. Its range has a finite dimensional span. And let me write that properly. I don't want span Fn, I want span Fns. So we get these finite dimensional spaces, and we should say in particular, each xn is separable. Whoop. My tablet's not liking me today. Finite dimensional spaces are separable because Rn and Cn are separable. So we can combine all of these separable subspaces into a large separable subspace. We call it x prime. We take the union of all of these xn's. Now the union of subspaces is again a subspace, so I don't need to take a span here, and I'll take the closure of that. Let me move this over. Drawing it too far to the right. Whoops. Ah, my tablet's really misbehaving now.
By union, you mean the direct sum, right?
No, just the union, actually.
So, but if it's just the union of subspaces, then it's not a subspace again, right?
Okay, let's be careful and write span. All good? I force it to be a subspace.
Yeah.
The subspace generated by all of these things, yeah. So we take the span and we close it to make sure that it's a closed subspace. Then this x prime is also separable. Because if we take countable dense subsets for all of these xn's and we just take the union of the whole thing, we still have a countable subset and it's still going to be dense. You can check that in more detail if you want, but this process of generating a subspace preserves separability because everything is countable. Now, since the functions fn converge to f pointwise, we have for every s that f of s is the limit as n goes to infinity of fn of s. Now, each of these fn's are in x prime by the way we constructed x prime. And x prime is closed by the way that we constructed x prime. So f of s is in x prime. All right. And this shows us that f is separably valued. And that's one direction of the theorem. If f is strongly measurable, then it's weakly measurable and it's separably valued. It's the easy direction, you could have guessed. Now what we want to show is that weak measurability plus separably valued implies strong measurability, which is a bit harder. So let's suppose that f maps s to x is weakly measurable. And let's just suppose without loss of generality that x is separable. Because like I said before, if x is not separable, but f is separably valued, we can replace x with that separable subspace without loss of generality and just consider that. So let's just assume that x itself is separable. And we let xn be a dense sequence. In x. X is separable, so there's a countable dense subspace. So there we go, we have a dense sequence. Now this is where it gets a little bit tricky. For every natural number n, let's define a function phi n, which is mapping the Banach space x into the first n elements of this sequence. And we're going to define it in such a way that for all vectors in the space, the distance between x and phi n of x in x is minimal among all possible choices. Basically, I think this is using the axiom of choice somewhere, but you take every vector in x and you say, let's just pick the closest vector in the first n and just assign it arbitrarily. Nothing about measurability, nothing, just it's a function. I think this is probably using the axiom of choice somewhere. I don't care too much about whether we use the axiom of choice or not. We are going to be using it everywhere implicitly. So we get this function phi, this helper function. We define it so that this is minimal, basically. And what do we do then? So since this sequence xn is dense in x, we have that the limit as n goes to infinity of the minimum of, maybe I'll just write it out first and then explain it. It's a little bit technical. If you fix, hang on, so this is for all x. Somebody needs to mute themselves. I don't know who it is. That doesn't matter. Anyway, so the sequence is dense. So if you take a vector in the space and you look at the first n elements of the sequence, eventually you're going to have one that gets sufficiently close to x by the density. So this limit of this minimum has to be 0. Does anybody not quite get that? Cool. And because this minimum is how we define phi n of x, what we get is that the limit as n goes to infinity of phi n of x is, hang on, I wrote a little mistake here. This xj that we define here is phi n of x. We define phi n of x to be the xj that achieves this minimum. So what we find is that the limit as n goes to infinity of phi n of x is x for every x. Is this relatively clear? Take it as given, it'll be fine. We use this to define our simple functions. We need to show that there are simple functions that are approximating f. Remember, we're showing that f is strongly measurable. So we define fn by fn of s is equal to phi n of f of s. So what's happening is that f of s is a vector in x, and phi n of that vector is the closest vector in the first n of the sequence. So we're kind of collapsing the function down to the first n elements of the sequence in some way. Remember that phi n is mapping into the first n elements of the sequence. So this is like a version of f which only has values in these first n elements. So it's simple. So to see that these functions fn actually approximate f pointwise, we write the definition. And we use what we had before, that the limit of phi n of x is x. So limit of phi n of fs is fs, which says that these functions fn actually do approximate f pointwise. It looks like we're done, but we're not. We need to show that fn is actually a simple function. Now, fn has got finite dimensional range. It's actually finitely valued, so it is basically a sum of characteristic functions, but we don't know that these characteristic functions are measurable. We need to show that fn is actually measurable before we can conclude that it's simple. So it remains to show that fn is measurable. This is equivalent to showing that the pre-images of the vectors xk are measurable. And this is for all k between 1 and n, because fn maps s into the first n elements of this sequence. So we just need to check measurability of each of these individual pre-images. So let's look at what this pre-image is. It's a set of points S such that phi n of fs equals xk, just using the definition of fn. This is the set of points S such that, just using the definition of phi n as this minimal vector in this first n elements, I'll write out what that means. Fs minus xk has to be the minimum from j from 1 to n of fs minus xj. Does this make sense? If you remember the definition of phi n, it should make some sense. This is a surprisingly tricky proof, I'll give you that.
One question.
Yep.
When you define phi n to be the xj that achieves that minimum,
Yep.
there might be several ones, so you have to pick one.
Arbitrarily.
Yeah, but therefore, the fact that phi n equals xk is not necessarily that condition you've put there. Because there might be another xk that also achieves the minimum, but it's not the one you've chosen for phi n.
Very good. Pick the one with smallest index k. You've got indices k from 1 to n to choose from, and suppose that you have like 2 k's that are allowed. Choose the smallest one.
But then in that second set you've put there, you would have to add that condition, like xk is the one that satisfies that, and it's the one with minimum k.
You're right about that. What I'm going to do is I'm going to finish the proof as if this is correct, and then I'm going to fix it in the notes because it's just little technicalities to make the thing work. Yeah, okay, the idea here is correct, but you're right. That's a little technicality.
It's much safer if you were to pick arbitrarily than you're immediately out of measurability.
Yeah. Okay, I won't think of that for now, but this is a good point, and I'll fix it up. The rest of the proof is you can assume this is correct, and then it gives you the idea. Good catch. So what do we do from here? We want to show that this set's measurable. We can see this set as where one function is equal to another function. So if we can show that both of these functions are measurable, then the set is a set of equality of two measurable functions, and therefore it's measurable. So we need to show that these two functions here, this left-hand side and this right-hand side, are measurable as functions of f. How do we do that? We use the separability of x. We haven't used that. No, we used it. We're going to use it again. We use it to get this dense set of vectors, so we have used it. Yeah. Since X is separable, there is a sequence of functionals, xm star, in the dual space, which is what you call a norming sequence, meaning that the norm of every x is actually the supremum over n, over m, I should say, of what happens when you pair x against this functional. The way you prove this is you just say, okay, for every x, you know that there's a norming functional out there. You know that there's a functional that makes it actually achieve this norm. This comes from Banach. Then you take the dense sequence that you started with, choose a norming vector for every one of them, and that's your sequence. By density, that will work. You don't have to know all the details of that now. Just trust me here, there's a sequence of functionals that is norming. So you can write your function, this right-hand side function we're trying to show is measurable. Or before that, actually, just if you look at this function, S mapping to this norm, fs minus xj, you can write that as a supremum over m. We test this vector against the functional xm. Right? So you can write this function is a countable supremum because this is supremum over natural numbers of measurable functions. So these functional pairing functions are measurable because f is weakly measurable by assumption. So this function on the left here that you want to show is measurable, you can reduce it down to these pairing functions and use a weak measurability, also using the separability. So in particular, when you take the function that takes the minimum over j of these quantities is also measurable because it's just a finite minimum of measurable functions. So if you look at your definition of this pre-image here, this is just saying that it's a set where one measurable function is equal to another measurable function. So it's measurable. And that was all we needed to show in the end. Okay. It is a bit of a confusing proof. Any questions about it?
So Alex, would you say this condition is extremely useful? Like we just use it all the time whenever we want to prove strong measurability. Like this is what we're going to go to.
Yeah.
More often than not. Okay. Yeah.
Basically, yeah. Because all of the functions we're going to actually deal with are going to, we have to work with strongly measurable functions, basically. Otherwise, our theory doesn't work. All of our theory is based on the fact that you can approximate functions in your classes by simple functions.
Yeah.
So we kind of have to work with strongly measurable functions. And sometimes we're going to be given a function in the proof of a theorem or whatever. And the first thing we're going to have to prove is that it's strongly measurable for any of our theory to apply. And so by this, we can just say, okay, is it separably valued? Is it weakly measurable? Okay, done, good. You don't have to find the simple approximates by hand. This theorem does the work for you.
Now, one more question. I know that pretty much all Banach spaces that you see out in the wild are separable.
Yeah.
Well,
except for the ones that aren't.
Not separable. Are you just like up, like you're without a paddle essentially, right? Like,
well, there's still some stuff you can do, actually. I'll make two comments on that. The first comment on this, what's a non-separable Banach space? L infinity is already not separable, but it's not so bad. And sometimes we're going to have to deal with bounded functions. In particular, I think for the stochastic analysis applications, L infinity is actually a space you deal with quite a lot. So sometimes you are going to have to deal with a non-separable space, but you're not completely without a paddle, I think you said, because most reasonable functions, say f from R to L infinity, are still separably valued. So even though your target space is not separable, a lot of the functions you're given are going to end up being separably valued. So they can still use this theorem. I was going to say non-separable spaces as well, because we're going to be dealing with UMD spaces later on, and L infinity is not going to be a UMD space because it's not reflexive. You can also take things like L2, or what you call little L2 of R. You can take an uncountable set and then put on the counting measure, which sounds like a bad idea, but you can do this and you get a non-separable Hilbert space. Whoops. Non-separable Hilbert space. So you can actually get Hilbert spaces, and sometimes they are natural Hilbert spaces that are not separable. So we do some analysis in non-separable spaces. It's true. But your functions that you deal with are going to have to be separably valued. Otherwise, yeah, then we really are without a paddle, then we can't really do anything. Or at least then you have to prove the strong measurability by hand. Oh, but then if you have the strong measurability, then your function is separably valued by Pettis.
Yeah.
So if you can prove strong measurability by hand, then you could have done it through Pettis if you found that it was separably valued in some way. Yeah, it's a very useful theorem.
Yes.
Yeah.
Thank you.
And now it's 11:50. That's perfect timing, pretty much. Any other questions? Okay. So the next lecture, we're going to talk about some consequences of the Pettis theorem, show that some functions are strongly measurable that are not obviously strongable, and move on to Bochner spaces. So these are these X-valued LP spaces that I was talking about in the first 45 minutes. And these are going to be defined as spaces of strongly measurable functions. So that's why this strong measurability notion comes in. Okay, I'll end the lecture. Oh yeah, one other question. Yep.
There's a question in the chat.
Oh, sorry. L2 of R, yeah, good question. L2 of, let's just write L2 of a set S. Just a set, no measure structure, nothing like that. L2 of the set is your standard L2 of the set, but your set has counting measure. So your norm of a sequence F, well, you think of it as a sequence, but it's a function. If F is mapping S to, say, C, then the L2 norm of that is going to be the sum over all n in S of F of n squared 1/2. And whenever F has uncountable support, this sum is going to be infinite. So it's the set of all functions that have countable support such that you have square summability on that set. And you end up with a very big space. It's non-separable, but it is still a Hilbert space. And you can do LP here as well, and you'll still get UMD spaces, but not Hilbert spaces and not separable. So yeah, weird space. It is weird. Yeah, but it's actually used. It's used in mathematical physics somewhere. Sometimes your things have to be that bad, right? It's used in probability, apparently. I personally have not used it, but yeah. Any more questions? I should keep a closer eye on the chat. If anybody ever asks a question in the chat and I don't notice it, somebody just yell out and I'll do it. But if that's it, then that's the end of the first lecture. Thanks for coming. I had no idea there were going to be so many people when I first advertised this thing. I thought I'd have like 10, but 32 signed up, which is great. And 27 came, which is pretty good. Next lecture is Thursday. I'm going to end the recording now.